Welcome back to your first lecture of week 12. This is Physics 360, week 12, day 1, scheduled for release on April 7th. Before we get into the material for today's lecture, just a rundown of assignments that are going on right now. You should have already emailed me your daily homework that was assigned last Friday and your first draft of your project. Due this Friday is just the daily homework that's assigned today for week 12, day 1, and that's just problem 1 from sections 2 and 3 of chapter 13. Coming up next Tuesday, paper homework 6 is due. That is a week from today. You'll submit that to me via email. And your last test before the final, test 3, opens on Friday, April 17th and will be due on Friday, April 24th, and there will be more information about that coming. So today we start chapter 13, and today's lecture is actually going to cover sections 13.1 through part of 13.3, not all of it. And this is a very interesting chapter to me because it's the most applicable in terms of physics. We're going to finally start working with actual physical systems and the actual partial differential equations that govern them. And we're going to be bringing together a lot of what we've learned over the course of this entire term into individual problems now. So before I get into the two differential equations we're going to discuss today, Laplace's equation and the heat flow equation, I want to kind of give you an overview of all of the differential equations that we're going to see this chapter and what they're all used for. The first of these is Laplace's equation, which is given as the Laplacian of u equals 0. Now here u can be many different things, and this is all outlined in section 13.1 in your textbook, so I'm not going to rewrite it all here, but I'll say it out loud at least. U here could be the gravitational potential in a region with no mass, the electric potential in a region containing no charge, the steady state temperature of an object where there are no heat sources in that region, or the velocity potential for an incompressible fluid that has no vortices, sources, or sinks in that particular area. The next one we might want to think about is called Poisson's equation, which is given by the Laplacian of u equals some function of x, y, and z, or you could write that function in terms of spherical or cylindrical coordinates if you want to. Poisson's equation is just like Laplace's equation, but it can be used in regions where there are masses and are charges and are heat sources. So when we actually have sources of whatever's causing this potential within the region we're considering, we would use Poisson's equation. And this function, f of x, y, z right here, is called the source density. So the source density would describe, if we're talking about electric potential, for example, the distribution of all of the charges in a given region. Next up is the diffusion or heat flow equation, which is given as the Laplacian of u equals 1 over alpha squared times the partial derivative of u with respect to t. This is the equation you would use when you have non-steady state temperatures. So when the temperature of an object is changing over time, but still with no heat sources, we would use the diffusion or heat flow equation. You can also use this equation for u representing the concentration of some substance that is diffusing. And here that constant alpha squared is known as the diffusivity. Next up is the wave equation, which is given as the Laplacian of u equals 1 over v squared times the double partial derivative of u with respect to t. The wave equation is used for the displacement from equilibrium of any vibrating object, or can be used for the electric and magnetic field components of an electromagnetic wave. And here, that constant v there gives you the propagation speed of the wave. Next up is the Helmholtz equation. And for the Helmholtz equation, F here is going to be the time-independent portion of a solution to either the diffusion equation or to the wave equation. And we will see the Helmholtz equation pop up over the course of our math once or twice this week. Last but not least, we have the Schrödinger equation, which is given as negative h bar squared over 2m times the Laplacian of the wave function psi plus v times psi equals I h bar times the partial time derivative of psi. And the Schrödinger equation is useful for finding you the wave function of quantum mechanics particles. So phi, or psi here, is the wave function of that particular particle. And we'll go into each of these in detail, but these are the 6 main equations we're going to spend this chapter studying, and these are all partial differential equations, meaning there are partial derivatives involved, so our solution methods have to be different than when we were dealing with ordinary differential equations. So we're going to start off by working with Laplace's equation, and we're going to consider the following example. We're going to study the steady state temperature in a semi-infinite two-dimensional metal plate. So we're going to arrange this metal plate as follows. The plate will have a width of 10 centimeters. So this distance right here is 10 centimeters. And the plate will extend up to infinity in the y direction, where all of this area that I'm shading in green represents the metal plate. And we're going to hold various sides of this plate at specific temperatures. If we're going to use Laplace's equation, we can't have any sources of heat within this metal plate. But that doesn't mean we can't hold the edges of the plates at certain temperatures. So the left and right sides we're going to hold at 0 degrees. And the top edge of the plate, which is at y equals infinity, is also going to be held at 0. And the bottom edge of the plate we are going to hold at 100 degrees. And the question that Laplace's equation is going to answer for us is going to be, what is the temperature of any given location within this plate after the system has reached its equilibrium state? That is what we mean by the steady state temperature. We're not looking at how this temperature changes over time, we're just looking at the equilibrium state. So our goal is going to be to find the following function. Find t as a function of x and y, the temperature of the plate. For the temperature of the plate, this function must satisfy Laplace's equation. So let's start to write out Laplace's equation. We have the Laplacian of t equals 0. And the Laplacian of t can be written like this. The double partial derivative of t with respect to x plus the double partial derivative of t with respect to y. So we need to figure out some way to work t into this equation. And we're going to make an important assumption here that will make our lives easier, and that is a very common approach in partial differential equations. We are going to assume a separable solution. A separable solution means that the x component, or the x portion, and the y portion of our function are independent of each other, so that we can write t as a function capital X just of x times a function capital Y just in terms of y. And this allows us to write our differential equation in a more helpful manner. So plugging this into Laplace's equation, we get the following. Capital Y times del squared of capital X over del x squared plus capital X times the double partial derivative of capital Y in terms of lowercase y. And the next step we're going to take here to simplify this a little bit is we're going to divide this whole equation by x times y, capital X times y, to get the following. 1 over x times the double partial derivative of x with respect to x plus 1 over y times the double partial derivative of y with respect to y gives us 0. And there's something very important that you need to notice about this equation that's crucial for understanding the next step here, is that this, the first half of our equation, is a function of only x. And the right half of our equation, not the right-hand side, but the second half of the left-hand side, is a function of only y. And these two need to add up to equal 0. Not just at one location, but at every location within the plate. So it will turn out that the only way for a function of just x to be added to a function of just y to give you 0 for every value of x and y is if each function is equivalent to a constant. So both 1 over x, del x squared, and 1 over y, del squared y, over del y squared, both of those are going to have to be equal to a constant. If you're not convinced of that, consider some location in here that satisfies this condition. If we add the x function to the y function and we get 0. Now keep y constant and just move x, say moving over to there. Well, y has stayed the same, so our y portion of our equation should not have changed at all. So if this equation is still going to add up to equal 0, that means the x portion of our equation can't change when I move x. And that means that each of these things has to be equal to a constant. So we can rewrite what we have in the following way. 1 over x double derivative of x equals negative 1 over y double derivative of y equals negative k squared, where we are going to assume that k is greater than or equal to 0, and this constant, k squared, is called the separation constant. In terms of why I made the separation constant negative, we'll see in just a second. If I had chosen a positive separation constant here, it will turn out that I won't be able to fit all of my boundary conditions. So, simplifying my notation a little bit, we now have the following two differential equations. Big X, its double derivative, equals negative k squared times itself. Here, the primes stand for a partial derivative with respect to x, but it turns out that since we wrote these things as a separable solution, that all of these partial derivatives actually turn into regular derivatives. So I'm going to overwrite these in a different color here to show you what I'm talking about, but all of these del's in these equations become d's, which is the helpful thing about this, because we've just taken a partial differential equation and turned it into an ordinary differential equation, or two separate ordinary differential equations. So here, the primes next to the x just refer to derivatives with respect to little x. And then the equivalent expression for y is y double prime, with the prime standing for derivatives with respect to y, equals k squared times big Y. So these are equations we know how to solve. And we get the following solutions. For x, we have two possible solutions. One of them is sine of kx, and the other one is cosine of kx. And for y, we also get two possible solutions here. For y, we get e to the ky and e to the negative ky. And now that we have possible solutions for both x and y, we need to go through the process of determining, well, which of these do we need, and which combination of them do we need, and what value of k do we need, and all of that has to match with the problem we're actually doing. So now we're actually going to go back and do something specific to the problem at hand. We need to satisfy all of our boundary conditions, and that's going to take us through a lot of the rest of this problem. So let's start to think through some of our boundary conditions. Well, one of the boundary conditions we have is we need our temperature to approach 0 as y approaches infinity. If we look at our y functions here, well, we have e to the ky and e to the negative ky. Imagine plugging in y equals infinity to both of those two options for our y function, and you can see that we're going to have to discard the e to the positive ky solution because it doesn't go to 0 at infinity. The next boundary condition we might need to satisfy is that the temperature needs to equal 0 when x is equal to 0. So here we're going to be able to discard our cosine of kx solution because cosine of 0 is not 0. The next boundary condition here we need to satisfy is the temperature needs to be 0 at x equals 10. In order to satisfy this one, we need sine of 10k to equal 0, which is only going to be true if 10k is equal to n pi, because sine is 0 for whole number values of pi in the argument. So this tells us that k has to be equal to n times pi over 10, where n is an integer, specifically a positive integer. Let's rewrite our function t that we have based on this information. So now our function t, that is a function of x and y, has an x piece of sine of kx, where we know the value for k. So we will have sine of n pi x over 10. And for the y component, we will have e to the negative ky, where again we know the value for k. So that becomes e to the negative n pi y over 10, all in the exponent. And we only have one more boundary condition that we actually need to satisfy here. And that is that we need the temperature to be equal to 100 at y equals 0. And hopefully just a little bit of staring at this will convince you that we can't satisfy this requirement just by picking some specific value of n. So we're going to need to do something a little more complicated here. Recall that if a function is a solution to a differential equation, and you have another function that is also a solution to a differential equation, that any linear combination of them is also a solution to that differential equation. So I'm actually going to rename this t I just put here t sub n. This is a basis function. We're going to take a linear combination of these solutions for a number of different values of n in order to satisfy our last boundary condition here. So in terms of the actual function t, we're going to write t as a linear combination from n equals 1 to infinity of, we'll call the constant b sub n, which will make sense in a second, e to the negative n pi y over 10 times the sine of n pi x over 10. But when this is at a value of y equals 0, we need this to be equal to 100. So t, evaluated at y equals 0, has to give you 100, and that has the following expression. The sum from n equals 1 to infinity of b sub n, the exponential goes away because you plug in y equals 0, and you get 1 for that exponential, times the sine of n pi x over 10. So, does this look familiar? I hope it does. It should. This is a Fourier sine series. Specifically, it's a Fourier sine series with L of 10, and the function f of x that we're trying to match is just a constant 100. So we can then find the values for Bn by doing our Fourier series stuff. So Bn has the formula 2 over L times the integral from 0 to L of f of x times the sine of n pi x over L dx, which, plugging in some numbers, we have L of 10. So the integral goes from 0 to 10 of f of x is 100 times that sine of n pi x over 10 dx. And it will turn out that we get the following values for Bn. This is actually a homework problem, is verifying this. We will get a value of 400 over n pi when n is odd, and a value of 0 when n is even. So this allows us to find the values for Bn, so we can go back up to our full answer here. This line right here that I've put the pink arrow next to is our solution to this problem. The only thing that's missing here is the different values of Bn. And now that we have those values, we can plug them in and write our final answer for the temperature as a function of x and y. And we get the following. 400 over pi times, and I'm only going to include two terms here, and it will turn out that two terms is actually a pretty good approximation most of the time for this situation here. E to the negative pi y over 10 times the sine of pi x over 10. So this is the n equals 1 term. And then the n equals 3 term comes next, plus 1 over 3 e to the negative 3 pi y over 10 times the sine of 3 pi x over 10. Plus ... because there are more terms. This is an infinite series after all. So this is the final answer to this problem. And this is how we use a separable solution, which is a major component of this process, in order to solve partial differential equations by converting them into ordinary differential equations. There's a couple of additional bits of complexity I want to discuss as it relates to Laplace's equation. One of them is that a semi-infinite plate doesn't exist in real life. All metal plates have finite dimensions in the real world, so when we assumed the plate extends to infinity in the y direction, that may be a decent approximation in a lot of cases, but it's not going to be exact. So what if we want to do a finite plate instead? So we'll have the top of the plate be at y equals 30, and we will hold that side at 0 as well. So we have this time a finite metal plate where we are going to hold the sides at 0 degrees, this top face at 0 degrees, and we are going to hold the bottom at 100 degrees. And we want to again find the temperature within this plate, the steady state temperature, as at any point, x and y. Most of what we did on the previous slide will still be applicable. We are still going to need to discard the cosine of kx solution, and we are still going to need k is equal to n pi over 10 in order to satisfy our boundary conditions at x equals 0 and x equals 10. But we can't discard our e to the ky solution anymore. Which means our function y has to be some linear combination of our two possible solutions there. Now, you could be forgiven for not being able to think of this next mathematical bit of trickery on your own, but it turns out that for the finite plate, it is easiest to do the following linear combination, where you take a to be 1/2 times e to the 30k, and you take b to be negative 1/2 times e to the negative 30k. And with these values for a and b, we get the function y is equal to 1/2 times e to the k times 30 minus y minus 1/2 times e to the negative k times quantity 30 minus y. And it will turn out that this whole thing is just the same thing as the sinh of k times 30 minus y. So if you plug in y equals 30 here, you get exactly what you expect. Both of the exponentials are e to the 0, so we end up with 1/2 minus 1/2 equals 0. So we have satisfied our boundary condition that t has to equal 0 degrees at y equals 30. So now we can write our basis functions again. So our basis functions, the functions we're going to take a linear combination of to find our final answer there, are going to be sinh of k times 30 minus y, where k is still n pi over 10, times 30 minus y instead of y, times the sine of n pi x over 10. So once we've applied our boundary conditions and been a little clever about the way that we write our function for y, these are the basis functions we're left with, and then we will define our answer as a linear combination of these basis functions in the following way. So I am using capital Bn here for a reason that will become apparent in a second. It will turn out that this coefficient Bn is not exactly the same as our Fourier series coefficient. So the only boundary condition we've left to satisfy is the bottom side of the plate. We already satisfied the two sides of the plate by choosing sine and taking k is equal to n pi over 10, and we satisfied the top through this definition of y in terms of a sinh function. So now we need to satisfy our bottom boundary condition. The temperature evaluated at y equals 0 has to give us 100. So let's write that expression. We still have the sum from n equals 1 to infinity. We still have Bn. We plug in y equals 0. We get the sinh of 3 pi n. And then we still have that sine of n pi x over 10 at the end. And now we are ready to actually define our value for Bn, the regular one from the Fourier coefficient. We are going to define all of this out front, since sinh of 3 pi n is just going to be a number, not a formula. We're going to define Bn is equal to capital Bn times the sinh of 3 pi n. Which means that we can go through and solve for the Fourier series to find our values of b sub n. And from our Fourier sine series, we get the same value of b sub n as before. It's 400 over n pi for odd n, and it is 0 for even n. But this is little b sub n, and we still need values of big B sub n, because that's what we're missing here in our general solution up here where I've placed the pink arrow. So this means that our values for capital B sub n are, for odd values of n, we'll have 400 over n pi, but also over the sinh of 3 pi n. And we will still have a value of 0 for even n. So this now allows us to actually write the form of our solution. Our temperature as a function of x and y can be written as the sum over all odd values of n. The coefficient Bn is 400 over n pi times the sinh of 3 pi n times our x piece times our y piece, so times the sinh of n pi over 10 times y minus 30 times the sine of n pi x over 10. And this is our answer here for this problem. And then we could keep as many terms as we need to get a good approximation, and you could just plug in your x and y to determine the temperature at a specific point. There's only one other complication here that I want to ask you about, which is, what if we had our metal plate, the same finite metal plate, but with two sides held at 100 degrees? So let's say we still keep the left side at 0 degrees, and we keep the right side at 0 degrees, and we still keep the bottom at 100 degrees, but now we also want to keep the top at 100 degrees. How do we do this problem? It will turn out that we don't actually have to start completely over to do this problem, and the space I have left on this slide is sufficient for what we're going to do. It turns out different solutions for Laplace's equation can be added to each other. So if we take the solution for our original setup, or not our original setup, if we take the solution where the bottom and sides are held at 0 and the top is held at 100 degrees, and we add that to the solution where only the bottom is held at 100 degrees, we will get the solution that is the sum of these two scenarios. So the walls are held at 0 degrees and the top and bottom are held at 100 degrees. So in words, so if we take the solution for this first arrangement and add to it the solution for the second arrangement, we will get the solution for the scenario I just proposed. And we already have this one because it's the problem we just did. And if we want the solution for this one here, well, this is our same solution for the bottom being held at 100 degrees, but just flip your y equals 0 and your y equals 30. So take all of your y's and replace them with 30 minus y instead, and you will get the answer to this first one. And then you can just add those solutions together to give you the solution for the situation where you have multiple walls at 100 degrees. The next thing we're going to talk about is the heat flow equation, which will tell us the temperature at any given location in our object as a function of time. So we use the heat flow equation when we want to know how the temperature changes over time. So the heat flow equation is as follows. The Laplacian of U equals 1 over our diffusivity, which is alpha squared, times the partial derivative of U with respect to t. And just a brief note here, we are no longer going to have T represent our temperature because that will eventually be the time component of our solution. So here U is the temperature. So we're going to do the same thing we did before. And this process will hopefully start to feel familiar as we do it a bunch of times over and over again for each one of these partial differential equations. We are going to assume a separable solution. So that means we are assuming that U, which is a function of x, of y, of z, and of t, can be written as a function we're going to call capital F of just the spatial components, times a function of capital T, which is just the time components. So plugging this in to the heat flow equation, we get capital T times the Laplacian of capital F equals 1 over alpha squared of capital F times the regular derivative of t with respect to t. I didn't make this change as early as I should have on the previous slide, but this is the point in the solution process where our partial derivatives become normal derivatives. Because in terms of the partial derivative with respect to t, only capital T depends on T. So we can just take the regular derivative of that, and f is effectively a constant in this situation. We are now, like we did before, going to divide by our overall function, which is f times t. And that does not stand for Fourier transform, it just stands for the function f times the function t. And we get the following. 1 over capital F times the Laplacian of capital F equals 1 over alpha squared times t times the single derivative of t with respect to time. And just like before, we have on the left a function of just our spatial variables, just a function of x, y, and z. And on the right-hand side of this, we have a function of just t. And the only way that these two can be equal to each other for every value of x, every value of y, every value of z, and every value of t, and every combination therein is if this is equal to a constant. So we are going to again define our separation constant as negative k squared. So rewriting the two parts of this equation, we get the following. For the f portion of the equation, we can rewrite that as the Laplacian of f plus k squared times f equals 0, and this is the Helmholtz equation. So it is the spatial component of our solution to a Laplace's equation problem. And then we can rewrite the t equation as follows. The derivative of t with respect to time equals negative k squared alpha squared times t. And this we can actually solve. This is a pretty easy differential equation. So we can use t equals e to the negative k squared alpha squared times t, time t. So hopefully it makes sense that we used a negative separation constant here, because if we didn't use a negative separation constant, then our temperature, or our time portion, would explode as time goes to infinity. And we don't expect the temperature of this, whatever object we're considering, to become infinity over time. We expect it to eventually work its way back down towards 0 of whatever temperature scale we're using. So we definitely needed a negative separation constant here. So this is kind of the basics of everything that we have. And to proceed any further, we need a specific problem. So let's bust out a specific problem. Let's take an infinite plate with a width of L, and we're going to hold one side at 0 and the other side at 100. And then that 100-degree side, we are going to switch to holding at 0 degrees, starting at t equals 0. So let me draw that for you. So we have a metal slab of width L. We are going to hold the left side at 0 degrees the entire time, and the right-hand side is going to be held at 100 degrees until we reach a steady state temperature. And then we're going to switch to holding the right side at 0 degrees, starting at time t equals 0. And what we want to know is we want to find the temperature in this slab at any given x value and any given y value at any given value of time. That's what we're trying to find here. So here are the steps we're going to need to go through to solve this problem. The first step is we need to figure out what that steady state temperature distribution is. So we'll call this function u0. And you can grind through the Laplace's equation stuff if you want to, or you can think about it a little bit and think that we have the temperature is only really changing for different values of x. We're probably not going to have any y dependence here, so we can actually scratch out this y here. And the temperature is likely to increase linearly. So you can verify this yourself by actually working through Laplace's equation, but it will turn out that this initial steady state temperature, a bird just flew into my window. that this initial steady state temperature that we're going to call U naught is just going to be equal to 100 over L times X. So the temperature linearly increases from 0 on the left side up to 100 on the right side. So we'll set that aside for now. We're going to move on to our next step. The next step is that starting at time t equals 0, whatever function we have has to satisfy the heat flow equation. The initial steady state temperature had to satisfy Laplace's equation, but the rest of what we're going to do, we want to know how things change over time, and that is determined by the heat flow equation. So in this case, we're back to exactly what we did before. We have this expression. Our Helmholtz equation is what the x component became. So we've already kind of done our separable solution here. But that Laplacian there, well, our function we expect to only depend on x, so we can rewrite our f equation as follows. The double derivative of f with respect to x plus k squared times f equals 0. And this has the solutions of sines and cosines. So f will have to be equal to, and let's just be explicit here, f is just a function of x, will have to be equal to either sine of kx or cosine of kx. And just like we did before, we are going to kind of beat this with our boundary conditions until it gives us a solution that matches all of them. So our next step is boundary conditions. And boundary conditions is really going to be most of the rest of this problem. So take a moment and see if you can work through this yourself to figure out what any of these solutions would have to look like, what value for k we need, whether we are going to have to discard any of our solutions. So one of our boundary conditions is that the temperature has to be equal to 0 at x equals 0. And based on this, we are going to discard our cosine of kx solution again. And we have the other side of the plate as well, that u has to be equal to 0 at x equals L. So just like before, we are going to end up with values of k that are n pi over the width of this object, which is L. So we now have our basis function. U sub n is equal to e, from down here at the bottom, e to the negative k squared alpha squared t squared becomes e to the negative n pi alpha over L, that whole thing squared with a negative out front, times t, and then our spatial component is just the sine of n pi x over L. And we are going to need to find some sort of linear superposition or linear combination of our basis functions. So we can actually write our solution here in the following way. We can define u, overall u, not u sub n, is the sum from n equals 1 to infinity of lowercase b sub n times our basis function, e to the negative quantity n pi alpha over L squared t, all in the exponent, times the sine of n pi x over L. So the boundary condition we're going to be trying to satisfy now is that at t equals 0, our function u must equal u naught. So in more mathematical language, that means that plugging in t equals 0 to our solution for u, we have the sum from n equals 1 to infinity of b sub n, the exponential term vanishes and becomes 1, times the sine of n pi x over L. And this all has to be equal to u naught, which we found earlier was 100 over L times x. So now you can do the Fourier sine series here to get that the value of b sub n is 200 over pi n times negative 1 to the n minus 1, which means that this will be equal to 200 over pi n for odd n and negative 200 over pi n for even n. So then we can finally write the answer to this problem. U as a function of x and t is equal to 200 over pi times the sum from n equals 1 to infinity of our constant b sub n, negative 1 to the n minus 1, over n, we already pulled the 200 over pi out front, times our exponential term here, which is the same as it was before, e to the negative n pi alpha over L squared times t times our spatial portion, which was sine of n pi x over L. So now we have the answer to this question, and we could plug in any value of x and any value of t and find the temperature of those locations as a function of time. Might be interesting to make graphs of these so you could have a visual of how the heat or the temperature of this block changes over time. So there's one additional complication here where this can get a little more complicated, and that is, well, what if the final temperatures are different temperatures? What if at the end of the day we're going to hold the left side at 15 degrees and the right side at 30 degrees? What then? How do we deal with that? And I will show you how that will work out. So what we're going to need to do here is to find the final steady state solution using Laplace's equation, and we'll use that to modify our solutions there. And then one of the lines from the previous slide where we first wrote the full form of our solution as u equals the sum from n equals 1 to infinity of b sub n e to the negative quantity n pi alpha over L squared times t times the sine of n pi x over L. We are going to modify this step of our solution to say u is going to have to be equal to this plus our final steady state solution. So this means that at t equals 0, we have the following. The exponential term vanishes, so we just have the sum from n equals 1 to infinity of our constant b sub n times sine of n pi x over L plus our final steady state solution, which we can rearrange to be u naught minus uf equals that same sum that we had before. So now this is just ready for our Fourier sine series. So rather than f of x just being u naught, now f of x is u naught minus uf. So basically, when your final state is not equal to 0 temperature, precisely at all points, then you expand the initial steady state minus the final steady state in your Fourier series instead of just the final state. I know this was a lot for one day. Things will get a little smoother going forward because we will be more familiar with the general process that we use to attack these partial differential equations. And what we use for our future equations, for example, on Friday we're going to talk about the Schrodinger equation, the wave equation, and potentially, if there's time, the steady state temperature in a cylinder, where we are going to see some Bessel functions come up. But it will go a little smoother and a little faster in the future now that we're more familiar with the steps that we take to solve these problems. So thank you for watching, have a good day, and please don't forget to post on Piazza or shoot me an email if you have any questions.